Hi, welcome to Raga Made Easy. This is chapter 3, part A. This chapter will be on basic Carnatic tuning. In Indian music, both Carnatic and Hindustani, we use pure tones, which means the tones are tuned in a different way than the Western equal tempered tuning. While it's possible to tune an instrument using a wrench and a tuning fork to any desired pitch that you want, the human voice is not designed to naturally do that. The human voice always chooses certain simple fractions of an octave while singing, and the human ear perceives these simple fractions of an octave as the most harmonious sounding. Now, that's the way God, or evolution if you prefer that word, has designed sound. When any note of any frequency is played, it also produces other frequencies which are of simple fractions of that frequency, and they are called harmonics or overtones and undertones. In Indian music, we use 12 such pure tones or Shuddha Swaras, they are called in India. Shuddha means pure, so we'll call it pure tones. So these 12 pure tones are all based on simple fraction theory and or harmonics. You may not have a clue as to what I'm talking about, but as we proceed and see the next slides, you will get an idea what I'm talking about. Now let's look at God's own pure tones. If Sa or the starting note C of any frequency, say, is 1 by 1, its octave will be 2 by 1, double of this. That means if you say, for example, choose a frequency of 100 hertz, it will produce an overtone of 200 hertz, 400 hertz, 800 hertz, 1600 hertz, and so on, doubling each time. And all these notes will have the same quality of the root note, which was 100 hertz, or the Sa. So only thing, it will be on a higher pitch. Similarly, it can be on a lower pitch, like if 100 is the starting, 100 hertz is the starting frequency that we are singing for Sa, the lower Sa will be 50 hertz, 25 hertz, then 12.4 hertz, and it goes on. Those are undertones. These are called harmonics. And between this 100 and 200 hertz, there will be other divisions. So before going into harmonics, we will talk about another principle. There are basically three principles with which the 12 pure tones and about 15 more microtones are derived. As you see on the screen, the most harmonious pitches between one octave, say fraction 1 by 1 and fraction 2 by 1, minor second Re 16 by 15, major second Re 9 by 8, minor third Ge 6 by 5, major third Ga 5 by 4, perfect fourth Ma 4 by 3, tritone Mi 45 by 32, perfect fifth Pa 3 by 2, minor sixth De 8 by 5, major sixth Dha 5 by 3, minor seventh Ne 9 by 5, major seventh Ni 15 by 18. Now, how did we choose these fractions? We did so by choosing the most simple and elegant fraction between 1 and 2. That is, between 1 and 2, there is first 3 by 2. There's nothing else between 1 and 2, right? Then the next octave is 2 and 4. Between 2 and 4, there is only one fraction, that is 4 by 3. 4 by 2 is again 2, and 4 by 4 is again 1. So we have only one fraction there, so 4 by 3. Then between 4 and 8, which is an octave, you should know that 1, 2, 4, 8 are all octaves. So between 1 and 2, it's an octave. 2 and 4 is an octave. Between all the fractions between 4 and 8 is an octave. Then 8 and 16, it goes in geometric progression. So between, say, 4 and 8, there are 5 by 4, 5 by 3, and 6 by 5. And they can be also 7 by 4, but in Indian music, we do not accept any septimal tones. That is, any fractions involving 7 or its multiples, we discard them because they don't fall within an even distribution of pitches. All these 12 pitches has to have some sort of an even distribution, like equal distance, almost equal, even though they are not equal distance always, like in the Western music. It has to be as close to the equal distance as possible, but the most harmonious pitches. So we don't use pitches that involves 7 either in the numerator or the denominator. Moving on with fractions that fall between 8 and 16, we will have 9 by 8, 9 by 5, 15 by 8, 16 by 15, which are sort of within the almost within the equidistance range and sounds very harmonious to the ear in relation to the tonic. And the last one is 45 by 32. That is between 16 and 32, the octave of 16 and 32. As you can see, that is the farthest away from in fractions from, say, the closest 3 by 2. So 3 by 2 is the perfect fifth, which is the most harmonious to the tonic after the octave. And then 45 by 32, the tritone, is the least harmonious in a pure tone scale. That is why the Roman Church musicians called it the devil's note. Now we can see that simple is elegant principle gives us these 12 pure tones. As you may have heard Professor Manjul Bhargava, the mathematician, say, if you tell a mathematician that the formula that they created looks elegant, they feel they're on top of the world. Well, similarly in music, when you sing a note, any note in a scale, if it falls in a very simple and elegant fraction, that note is like it's on top of the world. Now, we all know that it's too cumbersome to deal with fractions, its addition and subtractions. So, fortunately, mathematicians have developed a logarithmic formula to convert one octave in a more decimal fashion. It is not important to remember the formula or work with it. I'm just saying it so that if there are some geeks out there, they can get a better grip on the whole thing. So mathematicians decided the logarithm of 1 is 0 and logarithm of 2, if we set it as 12, they set it as 1200 because there are 12 notes. So we can get, say, around approximately 100 between each fractions. The formula is pitches in cents equal to 1200 multiplied by logarithm of any given fraction divided by logarithm of 2. So you will see that if you use that formula, as you know, the root or sa will be 0 cents and the octave sa apostrophe s will be 1200 cents. And the minor second re will be 112 cents. By the way, I'm approximating everything to have no decimals. All these will have decimal places also, which we don't need to remember. So minor second re will be 112. Major second re will be 204. Minor third ga will be 316. Major third ga will be 386. Perfect fourth ma will be 498. Tritone mi will be 590. Perfect fifth pa will be 702. Minor sixth dhe will be 814. Major sixth dha will be 884. Minor seventh ne will be 1018. That is all in cents. And major seven ni will be 1088 cents. This is God's own tuning. This is how God has tuned our voices to produce harmonious pitches in a scale. However, man's own tuning, they changed it. They made it equal tempered and made everything 100, 200, 300, 400, 500, 600, 700, 800, 900, 1000, and 1100 between 0 and 1200, one octave. Now, does it work? Yeah, it works when you're playing harmonically. That is, when you have to sound 2 or 3 or 4 or 5 notes simultaneously, like a chord, it works. But the human voice can never produce these pitches, that is 100 cents, 200 cents, 300 cents, naturally. You have to use some kind of auto tuning to change it. But that's actually screws up your voice. So if you are a natural singer, please, please, please tell these sound engineers not to touch your voice and convert it to equal tempered tuning. If you have made a mistake with one note, totally out of pitch, then you can bring it closer to equitempered, but not change the whole of your song in everything into equal distance. As you can see, the perfect fifth is 702 in God's own tuning, whereas it is 700 in equal tempered tuning, man's own tuning. So it's a minor difference. So 2 cent difference. Usually people don't recognize it. Whereas in major third, it's 386 to 400, which is a 14 cent difference, which is clearly noticeable to, maestros. And by the way, great musicians like Beethoven and Mozart and Bach, they all tuned the piano to a mean tuning where they had to have the major third perfectly on 386. So they always heard the perfect third as perfect major third, not as an equal tempered major third. They would frown at the fact that melodies are being sung or even harmonies are being done with 400 cents as the major third instead of 386. Again, I repeat, any melodic instruments like your vocal cords or a flute or a violin, always play by the ear and get to the pure tones. Next principle with which we find harmonious pitches in a scale is the principle that everybody talks about called the harmonic series or the overtones. We will deal with that in the next chapter. If you watched till now, I'm sure you're a geek in music, and I'm surprised you have watched it. So I'm thankful to you for watching it till now. So please do support this channel by sharing it with your like minded friends.